We're live. I better switch on. Oh, it's on. It's in talk. Okay, I hope somebody hears me. Welcome to the afternoon session of the Silicon Valley Fourth Interest Group. Those of you who are physically present and aware, and those of you who are out on the interwebs. I wanted to say that Fourth Day is coming. So if you are planning to be here and planning to present, I'd like to hear about it. If you're having trouble contacting me, well, you must make further efforts. We're going to do a little continuation of this morning's talk, since there was more to say and less of time to say it in. So without further ado, I'll give it back to Franklin.
Thank you. Okay, basically all I wanted to do is just show you the project running, just to see things real life. So the code is loaded on the chip. I'm going to plug in with the polyforth here. .300 list. Here's the beginning of the code for the project. I'll do a load. Everything should compile fine. And if we go to here, just to run the application while I have a logic analyzer running, so we could see what's going to come out. Final one. Here's the data. So we see what the structure looks like for the data on that one wire. And this utility lets me break it down for, it knows this is a reset. That's the presence pulse. Here's a match run command. Here's the data for the ROM ID and CRC data, and then reset again. I do it twice, and I get data back.
This is like a chip monitor type thing?
It's a logic analyzer.
That
it's running, it's a different hardware I have. It's from Salier Logic.
Oh, so you actually hooked it up?
Yeah, it's a.
Okay, this is like digital silicon.
Yeah.
You send your links and stuff to Dave for the notes. If you could send a link to that device.
Yep. It's
folks that are interested.
Yeah, this is I picked the right. There's many logic analyzers out there, but I picked one that could do not just what I wanted. I wanted several things, and they also give you an SDK to write your own if you need to. And it lets you, and it's pretty cool. You click on it, you could zoom in. It gives you time frames on the right hand side. The measurements, how it's coming in. You zoom in, zoom out, slide back and forth. It's actually good. It is. I did a lot of debugging with this once I got it up and running. It's $200, $250 for these 16 IO. Yeah. It's called Salier Logic. Right here. Yeah. Let's see updates. Anyways, it's available. It's pretty cool. These guys came out of college, made their own company, did it themselves. They're fighting up against the big boys, but I like it. You could swim in and out, slide back and forth, do multiple channels, and do different things with them, like SPI, I2C, and get it tells you what the data is too. It breaks it down to if you want to look at it in bytes or if you want to look at it in hex. So you don't have to do that. You see the data and
So you just added a wire.
yeah, connected it and put it on scan and then ran it. This is the data from the actual project. This is data analyzed on the bus.
A real cheap logic analyzer.
Good, cheap logic analyzer.
They are fast. Really, the more money you spend, the faster.
Oh, right, right.
Yeah, but they have some that are real good.
Yeah, I would recommend these guys. That's it. Just to show you, it ran real. There's the data, and we got data back if we do it again. Start it again, and do final 2 for the second device. There's the data for that stream. So if I wanted to see how things are booting up on the chip, I could put all that I need around it, SPI, serial, all that, and it'll give me a breakdown of all of this.
That's what I'm saying about this thing being a good tutorial. Not only is it software, but you also have hardware.
Yeah. Okay, thank you.
So on the radio this morning, or actually, I was listening to the replay of a radio episode of a quiz show, and they were talking about the origins of the phrase barking mad. So there's an apocryphal story about an insane asylum in Barking, London, England in the Middle Ages. And apparently if you went there, you were barking mad. Not just a little bit angry. But there are no writings in books from that time about people that were barking mad, so it's considered, dare I misuse the word, apocryphal. But seriously, folks, we're into the rumors, gossip. Yeah, on Car Talk last week, they were talking about Witzelschutz, or however it's pronounced. And apparently telling rambling stories and making inappropriate jokes and bad puns is apparently a mental disease. And none of you shall turn me in. So there. Or you'll have to find another program chair. That's an endless loop. You can go on like that for as long as it lasts.
Well,
All right. Okay. Do you want to stand up in front of the camera or just sit there?
Well, this mainly for the present audience. I'm about to become houselessness, and so I'm looking for someone who knows a family of empty nesters or otherwise having a room to rent in their home where I might find stable lodgings instead of month-to-month crashings. Because my months have run out.
So, rumors, announcements, gossip, cool stuff. Okay. So, on that cheerful note, there'll be a short lull in the action, I guess, while we try to get my laptop linked up.
I listened to two partisan radio programs from the Democrats and the Republicans last week. And I heard each of them expressing alarm over the tactics of the other. That the other party is always using unthinkable methods that are anathema to human decency. And it's the mote in God's eye that comes to mind.
I think they just didn't think of it first.
Well, no, they're constitutionally unfit. That is to say, using government as a club, using corporations as a club, each one seeing his strength as natural, and the opponent's recourse as unnatural. Because each of them despises the other's tool. Both have become irrelevant. If only there was some kind of thesis, antithesis to the work. They seem to have shock absorbers or otherwise protectors against paying attention to each other.
So I just found out that after much meeting on the SVFIG website, they do support Linux. So it's not just Windows. Cool. So they've got driver software for fairly recent versions of Ubuntu.
For those of you who didn't hear it, Sam was saying that these guys, Sele, have logic analyzers that do support Linux. The great thing, as Franklin said, is that they have an SDK, so you can write code for it yourself. And that has always been a problem for me with oscilloscopes and logic analyzers and other things that plug into my computer that, okay, you can capture this data and send it to an Excel spreadsheet, maybe, but can you suck in data in real time and act on the basis of some analysis thereof? And the answer is generally nope, sorry. The torturous path I've had to follow in the past is maybe to write some little bit or other for a LabVIEW call and suck things up with LabVIEW and then send it to my little module. And it's aesthetically unappealing at best. We were talking about one-wire devices, and this is Maxim's page that may make it to the meeting notes as a link. So here's a secure authentication device.
Design.
And here's another one.
And then, right there, deep one up. Deep cover secure authenticator. Yeah,
Wow, shot 256.
lots of.
Sure enough. Yeah, well, that's in Sha-na-na. Okay, thank you. Single channel, one wire master with adjustable timing and sleep mode. That makes me sleepy just hearing about it. Socket boards.
Sock it to me.
Oh,
I don't know. Life is going too fast for sockets these days. Here's a nice EEPROM 20 KB. I remember when I used to think like 10 megabytes was a huge hard drive.
I had one that big.
Here it is, silicone serial number. Oh, silicon, excuse me. Lithium battery evaluation kit. Well, that's the makings of some kind of dongle to verify your intellectual property rights or lack thereof.
64K app.
Yeah. That's the write-only memory. This is a new variation. It's the add-only memory, new variation of the write-only memory. I wonder if somewhere out on the interwebs there's still a copy of the WOM data sheet. I guess it would help if I spelled it more correctly. All right. With that mentioned, maybe we can take a short break and get Sam going.
Yeah, we have to start them up.
All right.
It'll take a little while, yeah.
Yeah. All right.
Not starting yet.
Slow starting. All right. I'm going to set this down, turn it
Testing 1, 2. Good. I have audio.
Yay.
Testing 1, 2. All right, so I'm going to begin. I'm going to say my name is Sam Falvo. I code in Forth. I'm also a home computer enthusiast, by which I mean I build my own computers from scratch. The presentation that you are looking at now is actually running on a homemade computer design called the Kestrel. It is technically a Kestrel 2. It has it has a 16-bit CPU of my own design. It is based on Steamer 16 though as a foundation. It has 32 kilobytes of program memory, 16 kilobytes of video memory. This looks like a text screen, but it's actually bitmap. Does not have any interrupts. It is running an elementary operating system of my own design called STS, and it is in fact running right now. However, when I tried to implement a dialect of fourth for it, inspired by E4th, I quickly found out that it didn't have the resources to simultaneously hold fourth and a user's program at the same time, even despite having 32K of memory available. Part of the reason is the common reputation that Forth has for being able to have an editor and a compiler and all this other stuff packed into 8 kilobytes of memory has some unstated assumptions associated with that. One is you're building it for an 8-bit processor. 2, you have a ROM on which you can depend on for I/O devices. And 3, you're working with a character matrix display. So all 3 of those conditions add up to having a very small amount of, what do I want to say? Very small amount of yaks, a very small number of yaks to shave, basically. So you end up focusing more on the problem rather than on user interaction. Since I built this machine as a graphical machine to start with, and since it doesn't have any convenient ROM, everything has to fit in that 32K chunk, including device drivers, including font, including keyboard decode lookup tables, and so on and so forth. And plus the relatively poor code density of the MISC architecture, which I'll get to in a bit. It basically left me very little room for growth. That's why I want to go to a 64-bit architecture. I'm going to skip 32 bits altogether. There are several reasons for this, not all of which are up here. One of which is pretty much by definition, all 64-bit machines are 32-bit machines anyway. They almost always have some way of doing 32-bit calculations. And by the time I finish getting around to doing this, everybody's going to know 64 bits anyway, right? So the writing's on the wall. I made the determination to do this back in 2012, and even by then, everything was 64-bit, 64-bit, 64-bit. Like it was pretty much everywhere. The nice thing about having a nice wide register set or word width like that is it largely obsoletes the need for a carry flag, which you'll be amazed at how much that complicates the internal design of the processor. Because people used to say, oh, 32 bits is enough, but you still ended up using that carry flag every now and again. With 64 bits, you almost never do. The numbers just don't get that high. Obviously, I can access much more than 48 kilobytes of memory. The Digilent Nexus 2 board on which I'm running this has a 8 megabyte or 16 megabyte, depending on which documentation you read, RAM chip on it. I will find out definitively once I actually build the circuitry to access it. Either way, it's much more than the 48K that's sitting inside the FPGA itself. And the other thing is there's an interesting problem with 64-bit processors, and that is how in the world do you manage your address space? It is so big that even multi-level page tables become gargantuan in size and become a monster to deal with. But yet you don't want to go back to segmentation because segmentation has its share of problems as well. So there's a lot of room for research and development in this, and I think I'd like to explore that science a little bit. So why not? Just go ahead and do 64 bits. So the question is, do I want to do this with MISC, minimal instruction set computing, or do I want to use RISC, reduced instruction set computing, or do I want to use CISC, complex instruction set computing? And all three of these architectures have advantages to them. and they also have disadvantages as well. So obviously the minimal instruction set computers are bar none the simplest to implement. I don't care if you're talking about a 1024-bit processor, you're still looking at a Verilog file that's going to be probably less than 400 to 450 lines of code. That's not very big. In fact, I would argue that most undergraduate students would be able to understand that in a couple of weeks. That's how simple that is. That's its core advantage. It has some issues with it. One of which is it's hard to get exactly 1 clock per instruction, or better than 1 clock per instruction. And that largely stems from its simplicity. You can pack n instructions per fetched instruction packet, however big that packet is. That takes 1 cycle to do. So it takes, to execute those n instructions, obviously takes n plus 1 cycles. And therefore, you asymptotically approach 1, but you never actually reach it, unless you can find a way to amortize the instruction fetch during an idle processing cycle. But the logic to do that is not insignificant. There's a couple of problems with MISC, though, that are more significant. Performance. I've actually been pretty happy with the MISC that I have now. Obviously, as you can see, it's updating this bitmap screen very fast. And this is only running at 12 megahertz. So this is really quite a performer, despite the 1.25 cycles per instruction. The real problem that I have with it, though, is almost every other instruction that you're executing is a literal fetch of some type. Now, I put this one in parentheses because depending on the specific MISC architecture that you're talking about, it may or may not involve a literal fetch there. For example, Chuck Moore's MISCs do not involve a literal fetch for an if statement. But for everything else, it pretty much does. And what you're ending up with is a lot of space being consumed by these literals. And this is the reason why MISC, once you go above a certain width, data width, you really cuts into your code density. So here's just pfetch1+, that just a tiny portion of the code sample that I had earlier. And it takes up 3 words of memory. Now imagine if this was 64 bits wide. It would be a massive waste of space, especially for just holding a constant 1, right? But even with just 16 bits, we're finding that 48 bits to just add 1 to P, and we haven't even stored it yet, which we're going to have to do at some point. So the nice thing with RISC is that you can do this in 32 bits flat. Now, in terms of performance, it's not much better than, or I'm sorry, in terms of code density, it's not much better than RISC. So we're looking at 24 bits to do a literal fetch and then some operation. But in the worst case, it can be worse than RISC. On average, though, it comes to about the same as RISC. So code density for 16-bit code, not that great. But when you widen it to 32 bits or 64 bits, it starts to fall off the cliff there. So, and yet, despite the relatively deep stack, in my case, I have a stack depth of 6 at present. The performance is only about as good as an accumulator architecture because you're always fetching and storing from memory. Your memory bandwidth is just enormous. And as I indicated, I actually do like MISCs. So why does the MISC work for Chuck Moore and the green arrays? And the answer is because it's running in a limited environment. So in this case, the limited environment is its advantage. It's its salvation. It has address registers, cache frequently used addresses. Usually these addresses are I/O ports. It uses fetch P+ and store P+ instructions, which are exactly like your fetch A and fetch and store A instructions, but it uses the instruction pointer as the pointer register. And those are used for global variables, which you don't use very often. But even so, you implement your variables as subroutine calls, which amortizes the cost of using those instructions. Which, in another sense, because the cores are so limited, you very rarely, well, I won't say very rarely, but I will say that the frequency of using a literal inline constant doesn't happen all that much, especially since you can do some amount of stack permutation as well, push to pop with return stack and so on and so forth. So for the green arrays architecture, it's ideally suited. You get very good code density, but it's not the approach that you want to take for something like the Kestrel. So now we're going to look at reduced instruction set computers. For a single issue processor, by which I mean every clock cycle you consume one instruction and you retire one instruction, it's actually not that much more complicated than MISC, at least in terms of Verilog source file size. I actually got to look at a couple of RISC implementations on GitHub and on OpenCores, and it seems like you can get the Verilog sources down to around 800 or so, maybe even down to about 600 lines of code. And very much like the MISC, opcodes work on registers of maximum width always. There's no such thing as add byte or, compare word or anything like that. That's actually significant for simplicity's sake, which I'll explain in a little bit. Loads and stores are responsible for sign or zero extension as needed. That means that the figures that or the data that you load from memory are treated as numbers. So if you load an 8-bit quantity from memory that has a high bit set, it will actually set the full 64-bit word to a negative value. It'll sign extend. And that way there you can do things like, instead of checking for bit 7 to be set, you do things like check to see if less than 0. So let's see here. And similarly, a lot of RISCs that you see today on the market, PowerPC, that sort of thing, you look at the instruction set that these things have, and they're gargantuan. 200 instructions, 300 instructions, some as many as 400 instructions. How can that be reduced? What does reduced even mean? Well, I did some research on this, and it turns out that the reduced part of reduced instruction set computing does not mean quantity of instructions. It merely means the amount of work that any single instruction does at any one time. The idea basically is to expose more of what would normally be microcoded to the programmer. Well, it just so happens that some RISCs can do quite a bit of work with very small numbers of opcodes, just like a MISC can. And in one particular case, the RISC-V architecture has as its core instruction set. There's additional instruction packages that you can include as well, but the core, the absolute minimum that you need to make this thing run, is only 47 integer instructions. That's not much more than most MISCs. It's only like what, 12 more instructions. So unlike the MISC, registers are named explicitly, by which we mean when we want to add a value, we say add register A to register B and put the result in register C. So it shares a lot of stuff with the MISC architecture, with the exception of explicitly naming the variables. It is, by its design, quite trivial to get one instruction per cycle. This is, in fact, the intent behind RISC. Back in the early 80s, when Patterson and Hennessy were working on their respective architectures, they kept asking the question, how can we get one instruction per clock cycle? That was their motivating question that drove the RISC technology. And also for IBM with the System 801. That was a demonstrator processor intended to eventually provide the backing implementation for an AS400 or for a System 370 later on. Because if we're going to replace microcode, it damn well better be fast, right? And it does this with a pipeline. Now, a pipeline comes with problems. Not so much with straight ahead code. In fact, the pipeline with straight ahead code is pretty much transparent. You can effectively ignore it. The problem with pipelines come when you need a branch. And the deeper the pipeline, the bigger the penalty you pay whenever you branch. So in this particular case, on average, instructions between branches tend to number between, I'm sorry, 5 minutes. Thank you. Tends to average between 8 to 16 instructions. So as you can imagine, branch penalties can add up pretty well. Now, if you do the math, it is possible to amortize the cost of a branch just like the cost of instruction fetches for MISCs. So in practice, it's not often a big deal. So I'm going to reset my camera here because it's almost out of time for this particular thing.
So are you charging another battery pack as you're taking this?
I am not. It would take all day to charge anyway. And that's my imitation clapper. Okay. It is a literal clapper, and I use literally in the literal sense. So the nice thing about RISC is also its Achilles heel, is that its code density is pretty well fixed at 32 bits per instruction. Now, different RISCs have different sized instructions, but on average, it's going to be 32 bits. The lack of stack permutation saves instructions, so you end up with fewer instructions that you need to execute. On the other hand, you also need to explicitly load and store your values to and from memory. The good programmer of a RISC will make sure to do that at the beginning and at the exit point of a subroutine, so that cost is amortized. Let's see here. The addressing modes are optimized for record-based access instead of array-based access. So it's a little bit different methodology for touching on data. But all registers are equally adept for use for both data and addresses. There's no need to load an A register just to access memory, for example. Here's a bit of an example of how a program would be packed into memory. It represents 64 bits of memory. And you can see at the very top, I'm adding 1 to P, and it's a single instruction at 32 bits. And then this second instruction here actually does the same thing as this over here, where we fetch the value of Q, and we check its high bit to see if it's less than 1. And then we proceed to do our program logic elsewhere. And the nice thing about the way RISCs work is that this instruction sequence will work for 16, 32, 64, 128, 256, 1024, however many bits you have in your register. The problem with the MISC is that it will work only for one data width. Generally not a problem because you're going from source code to your MISC architecture anyway. But if you're looking at binary compatibility or upgrade paths, that might be something to consider. So to summarize, RISC has unprecedented speed of execution, reasonably acceptable code density, but it also does have the advantage that you can create alternative instruction encodings as well. There's one in particular called head and tails, which actually gets you fairly close to 6-level densities for most RISC instruction sets. Speaking of complex instruction sets, this was actually when I was working on the 64-bit MISC design for the Kestrel prior to making the jump back to RISC. My quote-unquote MISC architecture ended up sharing a lot of attributes with CISC. So basically, I would fetch 64 bits of instructions, break it up into 8-bit slots. So you have 8 bite-sized instructions. One of the key things that I used to minimize code density was to use slot literals. So you would have these literal push instructions that took their value not from the next instruction word, but rather from the next slot in the instruction stream. And it was only a hop, skip, and a jump from that to packing instructions as tightly as I can without any no-ops whenever, you know, I had to break an instruction packet. And once I did that, that's when I realized that I jumped the shark to a complex instruction set computer. Even though the instruction set itself was very simple, the instruction decoder was massive. How massive? Well, it took 32 bytes of instruction prefetch queue minimum. It took 10 32 input multiplexers to be able to align instructions appropriately for the execute stage. You needed the logic to fetch steered instructions based on your current instruction pointer into the next available word in your prefetch queue. And you needed the logic to tell when to, but more importantly, when not to fetch another instruction word in case you were still fetching an instruction from the current slot. So it ended up being quite a complicated thing to work out. And of course, this whole architecture pretty much implies the use of a pipeline anyway. Oh, I forgot to talk about the why flags are a thing with complex instruction set machines. Basically, when you extend the data word size of a CISC architecture, you want to preserve your semantics for flags. So if a previous generation processor was only a 16-bit machine and you added a 16-bit word, you would expect the carry flag to be the result of your 17th bit. When you widen the registers, such as they did in the x86 or 68000 or whatever, when you widen those registers out and you do an add, suddenly your carry is being taken from the 33rd or 64th bit or whatever. You don't want that because that your program assumes that it's the carry out from the 17th bit. So that is why in CISCs, your operations are sized and not your loads and stores. I mean, they're sized too, but not like this. Not like they are in a RISC. So the benefit of a CISC obviously is code density, bar none. A CISC's claim to fame is how tightly it can pack instruction sequences in memory. So it's difficult, but not impossible, to get good performance by today's standards on a CISC. If you've got the transistor budget, you can do whatever you want. And to give you an idea of how difficult it is, an ARM processor today typically has a 6-stage pipeline, I believe, somewhere around 6 stages. An x86 that competes with it, you're looking at 24 to 25 stages. A lot of those stages are instruction decode. So what am I doing for the Kestrel? Well, I decided after discovering the RISC-V architecture, because at first I was going to do the complex MISC, CMISC, if you want to call it that. But then someone had a web page up and they pointed it out to RISC-V architecture, and I was like, oh, this looks interesting. Let me look at it. And part of my appeal to it is that it has explicit support for compressed instructions, which brings the instruction density down much tighter than you would think for most RISCs. So it is a BSD licensed instruction set architecture, which means that I can do whatever I want with this architecture as long as I give due credit to to the original authors. It is a 3-clause BSD license, I believe. The code density is absolutely no worse than the current Steamer 16. So I have a nice upper bound there, and it can only go better than that. Throughput is 2 to 3 times that of the MISC. And using heads and tails encoding, I can get near CISC level instruction densities. Very, very tiny. See here, the way I envision it, it will have a 24-bit external address bus to address the external RAM. There will be a couple of extra bits internally so that I can also address ROM and a couple of other things, especially I/O, but it won't be much more than that. From the programmer's perspective, though, you have 31 64-bit wide integer registers that can be used either for data or addresses. You have a 64-bit program counter, of course. You have no flags. There's no carry bit, no overflow bit, nothing. No process status register or anything like that. It will have fewer than 60 instructions. I will have more than the 47 that the base defines, just out of pragmatism, but not much more than that. And there's greater room to grow in every dimension. If I need a more compact instruction set, like I said, I can add the hat encoding. When I feel I'm ready to go with a user mode and supervisor mode and support for memory management, I can add that separately. The way the instruction set is designed, it's designed for modularity in exactly this way. And I expect pretty good performance out of that. And there's my ASCII art impersonation of the RISC-V logo. It's taken me about 2 years to get to this point where I've finally said, that's it. This is my CPU. This is what I'm going to do. And there was a lot of hair pulling, a lot of jumping ship between MISC and RISC, MISC and RISC, MISC and RISC. Anyone who's been on the mailing list knows that I've been deeply torn over which way to go. And I am naming it the SR64A. I would have loved to have included a logo of an SR71 there because of the obvious similarity, but yeah. So that's my thinking process. That's my conundrum finally resolved. And that's that. The Kestrel 3 will be coming soon, maybe within the next year or two. Any questions? It's all, everything that I do is BSD licensed. Everything. Yes.
You send your links and notes to Dave.
Mm-hmm.
You send instructions for joining your mailing list to have people join it.
I don't know that I have a mailing list, do I? I don't think I do.
Okay, you meant the SVFIG mailing list.
Yeah.
Comment about anybody that's been reading the mailing list.
Oh, yeah.
You were running the
Yeah.
test roll.
Oh, no.
Okay.
No. Yep, I'm sorry. I meant to, yeah, meant to say the SVFIG mailing list. So hopefully the next time you see the Kestrel and I give a presentation on it, it'll be a lot better than 640 by 200 resolution. And it'll probably have color. Here's hoping. Cool. Thank you.
There'll be a short lull in the action. I got a 15-minute break.
This is right now. This is all on the FPGA. This is the RAM chip.
Okay.
Eventually, I'll be able to access this once I have the bigger processor.
How much on that FPGA? How much more space do you have after you've done the,
For logic,
or just space, free space after you've done just what you needed?
well, it depends on how you measure it. So in terms of block RAM, I use 100% block RAM. In terms of logic, I'm using maybe about 1%.
Whoa. So you could array out each board.
Oh yeah, yeah. If I used the pins to drive this connector here, I could build out additional RAM. So I could have a RAM channel here. I could have maybe 1 or 2 RAM channels here. So you could actually build a nice NUMA architecture with this, and it would actually work pretty well.
Yeah, because since you took King's base FPGA design for called
The EP32,
EP32,
right?
yeah, just the fact that you can array them out in FPGAs nowadays.
Mm-hmm.
It's
The complication is the bus arbiter for that.
right.
But it's simple enough to get started if you use a just a like a round robin bus arbiter. It gets complicated once you go beyond that, but to start with, that's at least doable.
Right, right.
Why is this not packing? There we go. Yep, my Kestrel. I like this. This is already it's already shaping up to be what I want in a computer, because I can just turn it on, turn it off. No startup, no shutdown. Coming up with the slides for this.
Not much juice.
Yeah.
Hardly any. This was at 100.
Yeah.
It's at 66 now. Just
To 60. Well, you know, FPGAs. Yeah, and that's the other thing too, is that FPGAs are a power hog compared to dedicated silicon. So the fact that this drew barely any power.
I like to once you get to a good point, then you're thinking of radio.
I don't know if I'll be arraying out the processors. Something I would like to do at some point, but I'm thinking I'll probably get a bigger FPGA development board for that. Partly because the I/O pins on this, there's 40 available. Technically 80, no, 40, because it's 1 pin ground, another pin ground, another pin ground, right? So, but the 40 pins isn't enough for a lot of RAM. I would like to have at least 80 available so that I can route to different memory banks and stuff like that before. Hyper-threading is something I could probably do, though.
You want to be on the other side?
So,
You want to put this table? It's battery operated, isn't it? Well, no. That's not. Yeah, but you can unplug there, plug it in here, or I can give you the long cord if that's what you want. Or I could just stand here and make fun of you. Here.
That's a Surface Pro.
Let's see. It has a webcam built in?
On both sides. I don't actually.
Use it not only as a mirror, but as a magnifying glass.
Yes, I can. As a matter of fact,
Here's a
I still do.
carry the same sort of Hastings triplets that Doc. Row. Apparently carried his real life. One bus train across.
Yep. don't need that at the moment. So we switch this to actually transition. There we go.
Yeah, I think I went to 1 hour of the events that showed this year. Just bolted out the door. Worked.
It's actually kind of interesting. I think Mark actually feels quite challenged by diversified chips that the Berkeley group is for chips are using. These 64-bit diversified draws the same amount of power as the 32-bit as a 32-bit power. They do, but
It's like a you can get the closet.
yeah,
Never get it.
yeah. So I think they.
Ah, there we go. Finally.
I guess years before that, they stopped carrying more words.
I tried to stay away from easy titles because every time I go to the website, my whole computer slows to a crawl. They have so much JavaScript running on their site. It's just
Oh, where'd Minicam go?
Once in a while,
Did Minicam quit?
so it slows to a grinding halt. I don't know. I think it's Flash, container, SVFIG, Firefox browser. Northern antivirus. What? People's fine. No, I don't think so. Nobody's interested. I don't know why they would be. It's gonna be smart. Gotta hope they're being smart.
There it is. Okay.
It's
Suck it all up.
It's like those reports that show that NSA did nothing to stop terrorism, to even prevent terrorism, let alone stop it for a moment, fine. But damn it, we know what Kevin's wearing, which t-shirt he's wearing today. Yeah.
Remember, what is important?
And what we don't have,
Effort.
Yeah. It's an issue of priority.
rear camera. And transition there. There we go. That's a unobjectionable view. And now we're going to do screen share.
What's the point of listening to the radio? That's the same thing with Ultra. They knew that Kevin Cruz knows that about poetry. It's the work that you have to do to give a plausible alternative for how somebody can do that.
You were saying there.
Low class.
About the people from marketing with info were worried about.
Oh, with train rate, or with IntelliSys rather, what happened after that? That particular project was shot down. Then they came up with the regular design thing. They try to back up Chuck's design in traditional VLSI and actually made a chip that with a couple of variations. It could only be reset in one place. And then when in manufacturing, something got screwed up there and they had to fiddle with the reset because it wasn't redundant. Something was weird. But then they found that it was
a half to a third the speed, had 10 times as many transistors, and huge difference in power consumption. Huge. And Chuck, that was a year or two later. At that point, Chuck had garnered a little bit more authority, and he said, stop it. And they finally shut down. That was they had mentor various design seats for design software, eating up $1 million a year.
And
They
why
had
aren't
a dozen
we?
people that were all in the $200,000 category. It was just
There
a
we
soft
go.
touch for some people that were doing horrible
There we go.
as far as we were concerned, and it ate up millions of dollars. It had nothing to do with Chuck. Chuck was not getting this work. He was doing that either. So it was totally nuts. And the Green Arrays chip now, we've got some modifications, things we want to change, but it's not going to happen. The legal limbo that everything is still in will keep big players from coming anywhere near the chip, right? It'll all be small players. We can continue to have it made with money. All it takes is money to continue making what we've got. Anything more than that is going to take development time. Yep. All of that. Yeah, all that. At one point, we were working on a, what was it, 22, 23 nanometer.
Really?
Looking at it, well, no, was it 31? 1/6 of 180 is 30. So it's in that category, that range of feature size. And well, 1/6 the size, right? 30 nanometer instead of 180.
You're looking at me as if I remember any of this stuff.
This is all. This is after Green Arrays. This is
Okay.
the last couple of years. Somebody came in with a project for which they wanted the lower power that they would get out of a contemporary feature size, and so it took a bunch of finagling and stuff, but they managed to get the design, not the tools, but the scaled down. The information about the fab, about the scaled down process, and found that for the 1/6, so you end up with a 36 factor in size area. But it was only about a third or a quarter of the power. There's a lot more leakage at the smaller sizes. So the static component would go way up. And it would save power. And it would be a lot smaller, but not as much as one might expect. And it meant that because of the smaller size, the foundry, I mean, the stuff is built so that the package is meant to be filled with the chip. Otherwise, the wire bonding and
Somebody
stuff
wanted to buy EMC
to the
Apple.
from the frame to the chip,
I can't afford it.
get it to smaller things. And that would put 1,000, it'd put a
No,
huge number
oh
of
god, it was just there.
cores
I saw it
on the
on CNC.
part,
They
which
pitched it
would
an hour
draw all the
90%.
static
I
power.
didn't know that EMC owns 80% I thought
So either that or.
Not VMware. No, Microsoft has their own VM. Microsoft has their own VM. Azure is their VM.
Having to reduce it down to that doesn't help.
Is technology that
So it's unclear. The actually,
virtual device.
180.
Oh.
130
Okay.
boundaries. 180s, there's not so much going on, but the 130s would increase the static a little bit, and drop the dynamic a little
Oh, wow.
bit.
I didn't realize that that was a VM.
It might be interesting to do.
I mean, it was really primitive technology.
Right.
But,
Well, that was back a few years. In fact, that was when they became popular. Wasn't until 3.1.
It was introduced with 3.0.
But it was
characterization.
correct. 3.1 was the only time Windows was accepted.
Right. Because the mature numbers that they
Legacy was
publish
Right.
or exist in
Right.
forecast and all the different characteristics are meant for the spice models. And they don't reflect the actual values of this.
It almost has to. If you think about the technology, it really has to.
Based on, there's actually a physical simulation of the silicon rather than the whatever it is.
VMM 386.
The spice model
That's
does.
where it was.
So,
Cool.
I mean, the problems we had at the beginning with the 5 or 6 runs that they did,
Yes, but John, that article is what, not other John.
other than
That article is what
that was
I was reading just as I was starting that.
the simulator, the hard sim that Chuck had, the results of that were not matching the results that we would get back from the foundry in the chip. And the beginning, everybody thought it was Chuck's problem. And it wasn't until we really got better characterization values that, and plugged them in,
Okay,
and then the simulation matched the results from the foundry, and all of a sudden the chip ran.
Yeah, it was total rumor.
So
yeah, that's what I'm saying. I'm trying to say there was someone that said, no, we're not.
Chuck's design and his simulation model are good, but they have to have the right capacitance, resistance per square, and there was something else. There were 2 or 3 things that have to get plugged in.
Yeah, so
from
it
the-
sounds like that was just.
capacitance with small transistors, things like that, that have to get plugged in.
Right.
With appropriate values for the foundry, that after that it works. So,
there's not a lot of entertaining. Could they make their own?
if,
Oh, it's large
in
investors.
my mind, microchip technology, years ago, they got a fab.
Yeah.
And they have done all their own design in-house. That would be the ideal way to go. But it needs a whole different crew of people that are willing to, well, I don't even want to, I mean, we could use our design tools and stuff. We could, the array force kind of environment other people could use. We've shown that. We've got a number of folks come in that were working in hardware design and came in, and within a couple of weeks they were designing inverters and gradually getting bigger and bigger and figuring out how to do it. But like you found, it's a whole steep process to get it. Is your background hardware or software or both? Yeah. Yeah. It sounds like the rest of us. The problem for, well, with 4 people, the outside world, you have 3 or 4 popular design environments. And Eclipse, and people complain, but then they do something and you know, another version. The whole thing started with Emacs and Vi and so on, right? Within everybody that dabbles or even programs it, they like it their own way. And they can tweak the stuff, the environment they have it their own way. It's simple enough. You've got the whole from
They also have their own VM.
in the 80s, Chuck.
They also have the head of their ass, so
Designing his hardware.
I find it difficult to believe that Cisco in any way.
And everybody has that approach.
No, it's not Cisco. It's,
Yeah.
it's not Cisco who's got the other VM. It's Oracle. Oracle has the other VM. Oracle, not Cisco. Now, what does Cisco have anymore?
Just the routers and switches stuff, right?
Yeah.
And big iron routers too, not the small ones.
Yeah.
Right. They're legacy big iron.
The T1, yeah, the high level.
The 6500 other refrigerator size.
Yeah. And
It's been, the last time I traveled across country, it was really fun. Every few hundred miles across Nevada and New Mexico, even in Wyoming, Colorado, I went across the middle, but there'd be these big honkin' building things with microwave antennas and power line running, near the highway or near somewhere. There was a big high tension line. There'd be a power line going into these places. They were just boxes with big fence and barbed wire around them and stuff. You didn't know that they're, bait, the whole, what is it? What's the main loop kind of thing? They're just these
it's the phone infrastructure. Yeah.
for the
internet. Yeah, they're the internet hubs.
Yeah. And they're out, you can see for miles, that scattered all over the place are some cameras and things keeping track of that. You could not expect to drive up with a truck bomb and
Oh, no.
set them
No.
off.
You will be seen from miles away.
Seen from miles away. Like what?
You have to fly.
Oh, to be able to get it,
Put a truck on it.
No, you got to drop a bomb.
you'd have to fly in
That's
fast
like
enough.
that. It's either use the truck or you are the bomb.
One of the two.
Because the response time isn't going to be terribly fast.
Mm-mm.
But,
There's nobody within probably an hour.
right. But you will be noticed that you cannot expect to get out untracked.
Right.
Oh, man. You look like you're about ready to start.
I'm just wondering if we're going to wait until we catch up with the schedule, or
Did Franklin home for the day? I see his stuff.
He's still here.
Phone call. Okay.
Oh,
He'll be back.
We can wait. I was just wondering what your plans were.
Plan may be too strong a word.
That's true.
I have this written document.
And we're way ahead of it right at the
as
moment.
Part of the written document, it says, sometimes we don't quite stick to the written document, get over it.
Yep, that's what it does say someplace in
Yeah.
here. There we are.
Do we try to stick to the schedule? Well, yeah, I guess we sort of do.
Uh-huh.
Mic on.
Yes, the mic is on. We're just sort of talking and chatting and okay, Franklin's back. Do we want to do something semi-useful?
You might want to say where the idea for this talk came from.
You posted a
Link.
link to this guy, and why did I click again? I didn't really want to click again because I already have it clicked here of how to geek. And this is describing first Oracle's version of a virtual machine. I have never used Oracle's. I don't know how well it works. Microsoft also has one I have never used. Then this article goes into some more stuff. It goes into Cygwin. There are a lot of virtual machines around us. Sam was talking about a virtual machine himself. Most machines are virtual unless you're running on a real piece of hardware. And I had to move the entire projection thing. In fact, what am I projecting right now? On my screen. Yes, that's always fun. Because Google Hangouts doesn't work on Windows RT. Shame on them. They work on your smartphone, which is also an ARM processor, but not on Windows RT. Oh well. But Cygwin is another virtual machine. If you really want to talk about virtual machines, yes, it's creating a virtual Unix environment.
Oh, right, yes, that.
In that way, it is a virtual machine.
I was thinking of a processor, like you're emulating an x86 or an ARM.
No, you are emulating a machine. Not necessarily. A machine can be an operating system.
This is more generic, what you're saying.
Correct. And that is why my topic is very generic in this thing. That's why I'm starting here with this article. And that got me off into this list. And I've done most of these things on this list. And I will demonstrate many of them. I haven't used VMware Fusion. Not even sure what it's for, but oh, it's for VMware on Mac. There is also VMware for Linux now. VMware is one of the first ones that I'll demonstrate. It is a simulation of an Intel computer running on an Intel computer. So yeah, that's a virtual machine. It's not very virtual.
Well, it depends. If you have a 64-bit hardware, you can then run 32-bit.
Correct. Correct. And that
I've seen people run 64-bit systems on 32-bit hardware.
we'll get into how to do that in a bit. But yes, you can. If you had precisely the correct hardware, you can make that happen. Parallels was actually a virtual machine back when Macs were PowerPCs. Then you actually were emulating an Intel processor to run Windows. And that was very useful. I did run that back when I was working at Apple. So there's a bunch of them, and I'll show you a bunch of them. We now go over to my little thingy, and yeah, the fact that EMC owns 80% of VMware, that was curious. I'd never heard that before. And this little article here, says if you want to run 64-bit guest operating systems, this is the type of processor that you need. And no, they don't do it with a 32-bit.
No, I'm saying that I have seen it done at a severe performance hit, because modern day CPUs actually have dedicated hardware to optimize.
Right, right.
Yes,
That's what all of these processors do. And for a long time, I was running 64-bit Windows and could not run 64-bit VMware. And it pissed me off. And then now I've finally gotten a 64-bit system, or one of those processors here. And now I can run either a 32-bit virtual disk file or a 32-bit virtual disk file. And I think one of these windows around here has one of those at the moment. This is VMware's workstation, which costs money, but you can also get a free player that is free. You have to search for it a little bit, but on my blog here, I did provide a link for it. And then you can download a virtual appliance. And this is what I really like about VMware, is I can go to a marketplace that has just about any operating system that'll run on an Intel box. I'll bet you could find one.
You know, I find it interesting that they have this VM Planet. Fedora 14 was about 3 years ago.
Oh, many of these are old, but that's okay. Sometimes that's what you want to run, is an old OS.
That's like you run a machine.
Correct. This is a machine. And so,
And keep in mind that this also includes like 8-bit emulators and 16-bit emulators and stuff like that.
right. So you have, that's the nice thing about VMware, is you can go find these things and just download them and run them. They're wonderful for free. Some of the times the authors of these solutions, that's why this is a marketplace, sell them. Sometimes not for much money, but they do sell them. So you can find all sorts of things that you can run. I only have a couple up here at the moment. I have a 32-bit and a 64-bit. Now that Ubuntu's. And now that I can run a 64-bit, I almost never run the 32-bit. I keep it around just for yucks because I have a big hard disk at the moment. And so you can just start these things up, and this is all the hardware that it can access. And so you let that thing go there, and then I think this is Grub, yeah. And now you're just booting, as if this were a PC, booting this operating system.
So doing a virtual machine, you can do just about anything. You can say, I want to emulate this processor.
Oh, we're getting there.
Okay, good.
This is VMware. As I said, it's emulating an Intel processor on an Intel processor. So there's no emulation involved.
Right.
with VMware. And I don't know that VMware does emulation of anything. I don't know. As far as I know, they don't. But you end up here with a Ubuntu box, and we can go full screen, and it actually should have resized and didn't. Oh, there we go. Now we're up, and now we can probably go there. And now it does, as long as you have installed the tools properly, because VMware has tools that install in Ubuntu so that it knows the native screen resolution, so that now it can do full screen. And access all the hardware, there's sound, printers, blah, 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 blah. You end up with a lot of things that you would not have normally had. If we exit the full screen mode, you notice down here, here's my hardware that's all plugged in. And I can click on any of these things and actually, like there's sound, I can disconnect sound. And when it's attached to the virtual machine, it's disconnected in some cases from the host machine. And there's negotiations there. I have been successful in making various things work, mostly on USB. USB, like if I'm debugging Android, I'll typically go into a VMware to debug it because now I have better control in Linux on ADB than I do in Windows on ADB. But it's a transition, and life gets fun. But it's a normal Linux box. Runs a little slower, but it's a normal Linux box. The VM disk that I end up with, where am I here? If we go out over here and look at this PC, and I have two directories here. Now this one called VMDK is actually, if we click there, now we can see it over on the right hand side. That's 39 gig.
What?
It's a full disk. That's how much. Now, VMware does some interesting stuff with the virtual disk. It is actually allocated to be 80 gig in Linux, but it expands when it needs to. Doesn't contract automatically, unfortunately, but if I were to put 80 gig onto there, it would become 80 gig here. But as virtual, no, it's not. This is virtual disk. It's an interesting concept, and they're real fun. And there is one of these files, I think it's that guy. Oh, we don't want to do that at the moment. So let's shut this guy down. You all know what a Unix looks like, I'm assuming. So we'll just shut down. Because he is rather, I should show you that. Virtual machine settings. I have allocated 4 gigabytes of RAM. There's only one, I can give it more processors, 16. That would be interesting. And how many cores per processor. But it can sort of take over your main computer if you give it too much. These are all the various things connected to it. And you've got some options here on shared folders so that I can go out and look at my PC folders. I can't look at my VMware folders from my PC folders, or I haven't found a good way to do that yet. There are some utilities, they've been not so good in the past, and I haven't looked at that recently. But you can do some repair at the very least. What are some of the other things? That's about all that I look at there between those two. You can do a lot of different things. Mostly I played around with the USB stuff and add devices in. That's fun. But that's VMware. It's a nice machine if you want to run an Intel machine on your Intel machine. That's what that does. And now we can probably look at one of these files. Oh, that's not the right file. Is it that one? Maybe none of these will open directly for me. I may have to do a... Open up that guy first. And... Pause. Okay. No, that's not it. There's one of these files. Maybe it is the VMX. Yes. In this file, the VMX file, it contains all sorts of different settings that have all sorts of various different effects. If you don't like GUIs, this is where it affects everything else. So this is the virtual machine. You're controlling the virtual machine here. What I've done in these files mostly is change the name of the system that the file that it's looking for, the VMDK. But otherwise, you want to be sort of careful. You can totally screw it up and make it not work anymore. There's many ways of making those systems not work anymore, but screwing up the VMDK file is one of them. Okay, that's VMware. Any questions on VMware specifically? We know Linux. It's just another Linux or whatever version of Linux or various other operating systems you want. Yes, let's move on to QEMU. QEMU is what I consider more of a VM, and it is an emulator. You're emulating CPUs now. And I'm not sure if I ever did anything that says which CPUs they talk about, but you can look that one up. There's a lot. And it works on Linux or Windows. Obviously better on Linux. That's where it came from. It's open source. It's a nice little toy if you can figure out how to use it. I consider open source poor documentation, but depends on what you want in documentation. You have full source if you want it. I've used it various places. My most recent was playing with eLua at Renesis. Who knows if they're ever going to get there. So it's a cute little system for emulating another processor at the very root level. I've heard you can run an OS. I've never tried. It's doable. Getting QEMU to run is always an exercise in frustration because it's fairly cryptic on how you, and the documentation is like one page. One long page, but it's one document that tells you basically what all the instructions are for a given processor. Where I was playing with this thing the most, and what I have to demonstrate here, is the Open Virtual Machine firmware. I think that's what they call it. Open Virtual Machine Firmware Project, which is part of the UEFI project, which is itself a BIOS. If you don't know what UEFI is, it's what replaced Open Firmware at Apple when they switched to Intel. It's a bootloader. And part of what they've got there is the ability to, getting back to my blog, come on, to run a version of UEFI. What do we want to run? Yeah, that one. Now, where do I want to run it from? That will work. Right from a DOS window. Tiano Core is where most of the UEFI work has started. And so I'm booting into UEFI right now. And now I have a UEFI shell, which you will almost never see. Very few people, very few companies allow you this vision of BIOS. You do not get this, but it's there. It's usually there if you know how to get there. They just won't tell you how to get there. If I type exit, now you get something that looks more like BIOS. And this is what you've got. So all I'm doing is emulating BIOS at this point. It's interesting. It is a true emulator. And this is probably the closest I've got to a real virtual machine, what you consider a virtual machine. This is a virtual machine. So that one, power down, we go away. It's useful for various things. I've used it on and off over the years. A problem with a virtual machine, you don't have any hardware. You don't have anything to touch. You don't have a device that you're trying to control.
It doesn't,
Well,
it's literally all in itself.
it's in itself. There are ways of maybe emulating. I've looked into somewhat on QEMU. It's a possibility of emulating some external hardware that you may need to talk to. VMware can talk to almost anything that's plugged in.
I used QEMU where I was able to do a network install while I was inside there and be able to.
Oh, correct. I'm talking about you have a heart rate monitor sitting out here on the other end of your processor that you're emulating. I can't talk to that heart rate monitor.
Oh, right.
I can't talk to,
Still talk to USB.
I can talk to standard stuff,
Right.
but in what I do, I'm working on embedded processors that have little devices hitting off of them that I want to touch and do something with.
Yes.
I can't do that inside of a virtual machine very well. Therefore, virtual machines for me have been mostly academic.
Yeah.
This next one, I just found fairly recently, within the last couple years. And I think people remember that I once worked on Polyforth's Express. And have talked about Express from time to time. And I've been always unable to run it on a modern PC. It was a DOS program that Forth Incorporated emulated factories with, or controlled factories with. It was an early version of a SCADA program. And I couldn't run it. It pissed me off. Well, I found this little program that now I can say things like that. Ooh, I can't. Out. C building /Forth. PF. Yeah. No, I have to say CD Forth. No, I think I already am there. I just say PF. Oh, C colon. I remember how to do DOS again. PF. Hi, I have Polyforth. Ooh,
Well, those were the days.
this was the days. Express load. Mixer load. Actually, this is about how fast those computers ran, remember? Yeah, and I can just say run. Okay. And there's Express. A few little artifacts on the screen. Who cares?
So you recompiled all of that?
Yes,
Oh, yeah.
that was all from source.
On the fly. That's to load this, to load Windows 3.1 on.
Oh, yes.
One of those.
Oh, yes.
To that era.
Yes. This was a very, I liked this system.
When you think about what we were talking about a bunch in terms of graphics and stuff going on top of the old stuff, and the user interface, it's doing a damn good job of emulating a machine 100 times slower.
Right.
I remember the demos when she used to run, what's his name? would come in, the guy from Detroit area that had the cement, Amway.
Alan Furman? No.
No, it
No,
was
no.
Alan, but it wasn't Furman.
Yeah, there were a few customers, or quite a few customers around the world that we would come in and demonstrate this to or with. There was a cement mixer that was used in a lot. And now this is a classic virtual machine running inside of a virtual machine.
Exactly.
I'm actually a virtual factory running inside of a virtual machine running DOS on top of Windows 8.
Yeah.
Now this is cool. Fourth is your classic VM, and we'll get to that one next. No.
Express?
No. No. Talk to Leon. Talk to Leon. I don't think he will. The database package that this system used, I did get them to do public. That is out public now. Because this uses a lot of very interesting pieces of a machine that doesn't exist anymore, they don't want to support it. And I can't blame them. This is harder to support than just sending a disk out. And they don't want to touch it. I don't blame them. There's a support component to public domain. If somebody calls you on the phone, what do you say? I don't know. I've had this argument with both Leon and Elizabeth, and no, they're not going to do it. They're not going to do it. Oh, I would. I did a lot of work on this, and yeah, I would like to see a lot of this stuff come out.
This is why, like the GPL and the BSD license, there's a clause that says, this software, you use this software as is, without any like warranty or guarantees.
Yeah, yeah. We pausing again? But yes, this has some, interesting come on. Oh, you're not going to go in there. Historical trends, I know works. There we go. That's one of the nicest features it's got, is being able to put, you've got a scope built in. There were a lot of nice features of Express, but no, you can't have it. I can't give it to you. I like to occasionally run it and I'll occasionally talk about it. But no, that's as far as it goes right now. So that's this thing. So we've got DOS. A lot of people work DOSBox because it makes a great gaming platform. It's where all the DOS games you can play with. And that's why these guys exist. Okay. Oh, and here's some, these are a few of the projects that we did with Express. It doesn't talk about the cement truck or the cement factory that we had running. Doesn't talk about the golf balls that we were controlling the production of. It doesn't talk about the fiberglass factories that we had in South Korea and Mexico. Owens Corning was one of the clients. NASA was one of the clients. The space shuttle robot is NASA. Can't remember who the neural nets were, but you can go look at, each of these are links. You can go look at these. They're neat stuff. Now for something completely different. You mentioned Forth as a great virtual machine. Well, one of the more popular Forth, G-Forth, is a virtual machine. They actually produce the virtual machine that they use to create G-Forth. And that's what VMGen is. And it's a nice little virtual machine. And this takes Cygwin, which is in itself a virtual machine. Where am I? And they basically have a virtual machine here. Something like that, yeah. Are the instructions, and yeah, I haven't looked into it a lot. I played with it occasionally thinking that I could figure out more about array forth, that I could actually run it without array forth, but never got anywhere. Ran out of time, and now I can just say mini -h, and there's a virtual machine. It's a Java VM-like virtual machine called Mini. Oh, it's a Modula 2-like language with a small Java VM-like virtual machine called Mini. Don't we love Anton? And so we can do things like mini fib.mini. And it will run. Oh, really exciting. But it's the simplest virtual machine that I know about. Yeah.
Then my desktop died, and all I've got is this crappy laptop. So when I do get
Crappy laptops? I think laptops are better than desktops these days. Okay.
This crappy laptop. That's why I want to get one that a desktop that's got a whole lot of processors in it, so I can run it virtual machine.
Yeah. I prefer the portable. Another VM. How cool. Okay, we can look at that one right quickly here, because I've got, this is the VMs that I know about that aren't on the cloud. The next stage that we can talk about a little bit is the cloud version. How am I doing for time? Plenty of time.
Also, the battery is running well on the camera, so
Okay. In this case, the Hangout video is as good as, better than that, because I'm sharing the screen. And as Kevin and I were talking early this morning, the more speakers we get that will actually join Google Hangouts with us and can share their screens, the better our presentations will be. They're much better presentations if you share your screen on Google Hangouts. But you got to do Google Hangouts, which some people don't like. So on the cloud, probably the biggest these days is Amazon Web Services. I don't think anybody can touch them anymore. They're so big. In fact, they're now coming under attack for the amount of energy that they're draining in their server farms. Their server farms are very expensive. I heard Google is now looking at building them in the Arctic. Yes. Oh, it's all of the power goes to cooling.
That's why you find them, in Norway, places that got a lot of ice.
Yeah. Hey, I was surprised. I was actually.
It doesn't matter where they are, it still contributes.
It still contributes.
Energy that's-
I was really surprised that the Google barges that we've heard about weren't farms. That they weren't server farms. That would be perfect. Put them out in the ocean. In the water. And now you heat the water, but okay. Well, underwater, it gets a little bit difficult doing the transmission. At least above water. Well, now you have to plant them on this floor, on the ocean floor. They got to come up once in a while. Yeah, yeah. Yeah. Anyways. It's interesting what's happening with the server farms right now, and it right now is a fight between Google and Amazon, and they are fighting tooth and nail. I don't know who's winning. I like Glacier is how I got into Amazon Web Service. So I've got an account, and therefore I can go up and look at all of the stuffs that I can do on Amazon Web Services. Yeah, okay, fine. This is me. And this is all the stuff that I can do. Now I have no clue what any of this stuff is. Yeah. There's Glacier. I know how to use Glacier. Glacier's cool. You have pennies on the gigabyte for storage. It's pennies on the gigabyte. Better than Google's doing at the moment. But they keep on fighting back and forth. The S3 is closer what Google offers. Is the storage type of stuff that Google offers. And
So S3 is real-time access Glacier is more of a backup system.
Right. Glacier takes approximately 4 hours to go on or off. You give a request that you want this data back. 4 hours later, you will get it back. You give them data, it'll be 4 hours before it's actually in their farm. So it's really slow storage. That's why they call it Glacier. But it's pennies. It's wonderful. So, getting back to where I was. Where was I? Back over here. That gives you, Amazon Web Services gives you a virtual machine in various different formats. That's all of these little things that they're giving you here. Most of those are virtual machines in some form or other. S3 just happens to be just storage and storage gateways, but EC2 is virtual servers. That's sort of what you want. Then with a virtual server, you've got Turnkey Hub, which allows you to put a virtual machine, a OS, onto one of those servers that now, and back in the day, back in somewhere around 2011, when I first got onto Turnkey Hub, they allowed me to do it for free. That I could create a virtual machine, a Ubuntu, load it onto an Amazon server, and run it, and SSH into it, and have a machine for free. Well, at that point, for free. It's no longer for free. These are something that a lot of people like to have. Right now, you get 750 monthly micro server hours free for up to it. No, this was back in the day. You get 750 monthly micro server hours free for up to a year with free usage tiers and at 2 cents an hour or $14 a month, and not bad fees. It's gotten more expensive. That's 2 cents. That's half a cent an hour, yes. Yeah, and that's just their marketing stuff. And it's now $10 a month to do anything. And I decided I didn't, for this talk, if you're interested, you can figure it all out again, because it's part of the problem with this stuff is it's changing as they come up with different ways to monetize it. And therefore you have to, it's changing underneath you. Yeah, nothing's stable here in this stuff. You need me to make this bigger?
Yes. There is nothing stable.
There is nothing stable here. We're now in the cloud. It is changing faster than we can keep up, or than I can keep up. There are people that this is their job, that they keep up with this stuff.
Once your instances are created, though, it's stable. It's
Yes.
when you need to create a new instance that you have to look at the other options.
Yes, yes. If you save an instance, I could have done that back in the day. I didn't ever pay to save an instance. I always recreated an instance on the fly. And that was free, but it changed. Now, Elastic Beanstalk is now something that you can do right inside of AWS. That's one of Amazon's features. You can create your own instance, and they've got sample apps. Those are the big boys. This is Amazon. These are the big boys. They're making tons of money doing this. They're the ones creating most of the web pages that are out there these days. Rackspace is another small player, actually. I know you're not, but compared to Amazon, are you getting bigger?
They are in an unmanaged hosting situation. Where
Yes.
you create your instance and you're on your bloody own.
Yeah.
That's it.
Yeah.
In terms of managed cloud computing, we are the biggest.
Yeah, that's true. That's true. If you want a company to manage you, Rackspace is one of the top.
We have unmanaged capabilities too, but I mean, we can't compete with their pricing model, so we don't bother going to that.
No.
And realistically speaking, there's enough market space for all sorts of players. I mean,
Oh yeah.
Microsoft has their own Azure-based system, which is, I understand, is very good model for some types of companies. But again, not for all. So
Right.
it really does depend on what you need.
Right. Exactly. And you can find a way to accomplish just about anything you want to do. And
Oh, and if you want to do meteorological or astronomical simulations, there's a company out there called Nebula, which is an interesting history because Nebula it's an OpenStack provider, and when you purchase a virtual machine instance from them, we're talking hundreds of cores, terabytes or petabytes of RAM. You know, massive compute clusters. These things are designed for simulation.
Yeah.
And
Yeah.
big data
Or
applications.
analyzing.
Right.
Yeah.
So, but the guys who started Nebula worked with Rackspace to create the OpenStack standard. So Rackspace and Nebula, I mean, we're not related as companies, but we have that common heritage.
Right.
Between us. So, and as maintainer of corporate cloud, I've worked with them very, very often.
And I just see that growing and growing. I do not see, we're nowhere near the peak. At least I don't think we're anywhere near the peak. And it's just going to keep on growing.
And once we get to the Internet of Things, then it's actually going to scale down as well as scale up.
Right, right. It's going to be very interesting, at least from my perspective, of how the Internet of Things affects all of the cloud, because the cloud's so deeply involved in that. It's going to be amazing. Jolly Cloud was more along what I was thinking of, or what I was looking for as a VM in the cloud. I want to have a system where I can just call up the cloud and launch an operating system. Launch a system for a fairly decent price. Jolly Cloud was an early one of those. They ran out of business. It's now open source.
They sold it, right?
No, they did not sell it.
Oh, Jolly Cloud is now open source.
Jolly OS is open source. Jolly Drive, they are still doing. What they found out was that you can make money from storage. There is a ton of money to be made from storage, as Glacier can attest to. Glacier's one of those. And everybody is willing to pay some amount of money for storage. People were not willing to pay to just run an operating system, just replace their computer in the cloud. There's no money there yet, or not much money. Not enough for Jolly Cloud's business model.
You know, that does make sense, because how long do processors, what's their lifetime? You understand? It's the data that's.
It's the data that you want to save. but it's the OS, the instance of your computer that we have not made that transition where enough people are willing to pay money for. And the pay model has not been well established yet. And so Jolly Cloud was one of them. Now, there's a bunch of links to various other ones that are out there right now, 7 classic versions of Windows and Mac OS that you can run. You can run almost any version of an OS in some version on the cloud. Somebody's got an instance of it running. How do you manage your data is one of the fun parts. And this is one that I just ran across. This is a new one that I just came across. Oh, $1 a month. Wow.
Did they change out from under you?
Yes. As I said, they're new. And I think you're going to see a lot of these things happening as people try to figure out how to monetize it. They've got to come up with a business model where this works, where I'm getting real tired of buying a computer every couple of years. And why do I have to keep on buying a new one? Let somebody else do that. But they're going to have to figure out the monthly price of that. And I'm going to have to be willing to pay that.
And you want to make sure that when you transition to the new one, all other stuff.
And how much am I being charged for storage too? And am I being charged for storage of the OS and applications too? And how private? There are tons of questions we've got to get resolved.
Jump on that and say, well, this is the way to the future.
I agree with them.
Well, I agree, yes, but it's like, yes, it is the way to the future. Why are you jumping on it now?
And how much do we have to give up to go there?
We shouldn't also ignore the past, because this ironically ties in intimately, strangely enough, with most of our operating systems today that we're running on these VMs. Let's not forget that Unix is the outgrowth of AT&T engineers becoming disenfranchised with Multics, which was intended to be a computing as a utility resource. Yes. Right. So we are ironically using a single user operating system. What was intended to be a single user operating system. Back then it spelled UNICS. It eventually became UNIX. Marketing got involved. To implement the dream of the brainchildren of Multics. Right? This is IBM's dream from the mainframe days. This is GE's dream back in Multics days. Right? So we need to not forget the past. Like, why do we have personal computers today? It's because of the failures of computing as a utility.
Yes.
Right.
There's room for both.
There is.
But
And they're finally getting the distributed computing environment usable. It's the only reason we have personal computers is because the distributed system was so bad.
Yes.
Is IBM said, oh, here, have this, and was able to monetize you buying your own iron.
Yeah, I can remember when we went to at school, we had our computer deck, punch cards, submitted it, and come back several hours later. I was lucky because one of the graduate students was running an 11, maybe 1170 or something like that. And he says, oh, you're just running carbon, I'll put you in front of the queue.
Yes.
Yeah.
Yes.
In a reading room. But then all of a sudden, hey, I don't have to deal with these computer operators.
Exactly.
And I got my own.
Right.
Going, that's good. Because
And
I was doing astronomical research, I was doing basic programming, and I was doing a lot of it, and I was running out of CSUs. You know, so I had to keep going back to my professor and said, more,
yes.
want your stuff more.
Yes, I totally drained my account in college by putting a microprocessor emulator into an endless loop.
Oh, yes.
So that's the other thing too, back then, you were allocated a finite set of computing units.
Yes.
Nowadays, it's an arbitrary set of computing units, but now you're charged half a cent per unit that you use. All right, so
Some cases, the business models that I'm seeing right now are not computing units, they're time-based, a monthly fee. No, it's not. No. A monthly fee means you can use as many computing units as you can squeeze into there. But it's time-based. It's not processing-based. And it's a difference in monetization.
I will argue that it depends on the cloud provider.
Yes.
Because I've seen cloud providers that do count cycles.
Okay. Okay. I wouldn't doubt it. I wouldn't doubt it. You're going to get both. And
Because think about it, if you're running an application on a machine, VM or otherwise, and you do put it into a busy way, just an endless, but a busy way,
yeah.
you're going to suck power on that processor. You're going to suck performance from other tenants on that machine. So,
And they have to have a way to shut it down and or charge you for it in some way. And they do have more off of how many users do you have? How many user streams do you have at one point in time? And that's the more common that I've seen. Is. But yeah, they are figuring out how to finally accomplish what they started out to do. And we're going back to the old days of distributed computing instead of isolated computing, which we got with the computer. We've gone back to now we're all connected. Not a bad thing, but it's just different.
I'm just saying, let's not forget the history of it. Yeah. Because as soon as you forget the history of it, you're going to end up with the new IBM, becoming the new mainframe monolith.
Or Amazon in this case. I don't know how much longer I want to pay for that.
I don't, because I don't really trust the companies. You know, how can I, because remember, when you're on the cloud, you have to make sure that your ISP can get you.
Oh, correct, correct. You've got an,
It might not be if I still want to work.
you've got a connection problem. I agree with you. But the maintenance of my personal iron is high.
Really?
Yeah, depending on how much I want to spend. I have to buy a new computer every couple of years.
I'd like to have a desktop with 64 processors on it, so that I can run different virtual machines that I can run, that
Yeah.
I have control of.
Yeah.
I keep track of them all.
Yeah, it's my I'm tired of keeping track of all of that. I was like that. I've been there, done it, and I'm tired. I don't.
I do, because I don't anymore.
I don't, yeah.
You used to go to a dealer.
I could tear down an engine.
Oh, you got that?
I
Oh, you know, so they go,
stopped when that first time I tried.
67 VW van, I tore down and messed with, but
Yeah.
85, no way.
Yeah. It is becoming too much work and too complex of a system.
Practically against the law to work on your own car, because anything you do that changes the emissions, you have to
Yes.
bring it back and have it respond.
Correct.
Yeah.
Correct. And there's reasons for that. We all have to live on this planet with the air that we share.
That's why I agree with that.
But the states to the east of Nevada have to share your air. So, I don't know. I like seeing these virtual machines come. I think it's going to be very interesting as they figure out the systems. Do I worry about connecting with them? Yeah. Part of my commute is on Caltrain, where I do not have a solid connection all the time. It's not there.
I thought they would run right in the
No, not on Caltrain. It's-
Amtrak.
Amtrak probably does, and they're talking about the electric trains for Caltrain. And there I'm hearing that they are going to do built-in Wi-Fi.
The Highway 17 commuter bus has Wi-Fi.
Oh, a lot of them do. A lot of them do now.
There's so many geeks, commuters going
Yes.
from Santa Cruz to
Yes.
the valley.
Us. Us. Yes, we're commuting. And I am commuting to San Francisco, so I've got to work.
Yeah.
That's way too much time. I've got to work. So, any questions? We've talked about a lot. Am I done?
Sure.
I can be done at any point.
All the way.
Have I talked about enough of these?
Oh, if you go to RIS,
Oh, that's right. Which one?
go to riscb.org/.
R.
RISC.org/media. While he's doing that, I wanted to say this whole thing was started by a website that has interesting articles from time to time. The most recent one that I was interested in talked about booting Ubuntu not from a flash drive, but rather from your hard drive, as if it were an ISO image that was on a CD or DVD or your flash drive. You can boot right off an ISO from your hard drive.
Yeah. Oh, did I? Yes.
Oh, I will try to put it on Google.
Boot Linux. Is that what I'm need to do here? Oh, there it goes.
Give it a couple of seconds to
Oh, and somebody on my blog was asking, can they boot Linux or Forth? Can we run Forth or Forth-like language in the cloud? Would it be scalable? And I sort of pointed to Brad. I don't know how scalable Knackle is.
There are contexts in which it can be used in the cloud.
And I don't know what he means by scalable, what he wants to be scalable. Yeah, what does this really mean anymore? And we're still booting. Oh, BusyBox is coming in. But what I was going to just point to there was, fine, if I want to run Forth, there's Forth. I can run Forth anywhere. So yes, you can run Forth on any virtual machine. It is a virtual machine. Virtual machines can run virtual machines.
Virtual.
Literally. There we are.
Who is running Unity-A? That's not too bad.
Oh, yeah.
So this is actually running a virtual machine in JavaScript on the browser.
How many virtual machines do we have running right now?
And this is a more advanced version of the processor that will be going on the test.
Okay. Yeah. I mean, virtual machines are all around us right now. And yeah.
Let's not forget the perennial favorite for virtual machines, Java.
Right. That's probably the most ubiquitous one right now. It's running everywhere. Almost
Too many places.
on every phone, every smartphone.
Every Android especially.
Yes, and I would bet every iPhone too. I think they're also included, that you also have a Java virtual machine on those. It's starting, I can't say that it's on wearables. It's why I like wearables, is that they are small enough now that you really can't use much of an OS at all. And I like that. But yeah, that's the bottom of the Internet of Things, is the wearables and all the sensors.
Or cyborg.
Well,
Does it make you any more of a human?
No, it's going to make it so that you don't have to be as much of a human.
Yeah.
Humans are fallible. Humans die.
You have to work at being a human. And I'm lazy, yeah.
Yes,
Oh, yeah.
yes. Computers allow us to be lazy.
I only do that in my work. When you interact with people, you don't be lazy.
I think it's more correct to say that computers enable us to be lazy. But when we're interested enough, like for example, I have to drive pretty much an hour to be here.
Yes,
I'm carrying a can, got my kettle,
yes,
a fair amount of work because I derive personal benefit from the interaction of that interaction.
correct.
But at work, I'm like, let the computer do all of it.
As much of it as possible. Yes. And I agree with you there. My goal on any job, any computer work, is automate as much as possible. It's got to be automated. If it's not, then why am I working? So, anyways. Okay, now am I done? You keep on saying that. Where am I now?
Start closing down browser tabs.
Oh, there, the infinite screen. We are done for today. It's time to go home and have a life.
The green thing around it, it's coiled.
Stop sharing my screen. We are now on to that. I can go back to what screen and wave goodbye. And I have cute transitions now. Bye.